Okay, our next learning goal in this module one or topic one, be familiar with the four molecular modes of motion and how they connect to the EM, that's the electromagnetic spectrum, and quantum mechanics. Okay, let's do it. So recall that this was, we talked about this in the beginning of Chem 361, but just to go through it again, here we have our four molecular modes of motion. And something that we want to discuss right away, there's no mysterious like meaning or definition to quantum mechanics. Quantum means quantized. So it's as simple as that. So quantum means quantized. Okay. So if we look at the electronic levels, for example, where down here at the bottom, that might be level 1, the ground state, level 2, level 3, level 4, etc. As you can see with the electronic levels, they get really crunched together as they go up. And we'll talk about why that is in due time. And if we were to look at a typical energy spacing, let's say between level 1 and level 2 of an arbitrary atom or molecule, this could be anywhere between 1 and 10 electron volts. Okay, so that puts us on our electron volt scale. So that is an EV. So if we were to zoom in to this first level, or really any one of these levels, we would find a whole variety of vibrational levels. And as we shall see, those are linearly spaced. And if we look at a typical energy spacing between level 1 and level 2, for example, that's about 0.1 to 1 electron volts, so significantly lower in energy. And now similarly, if we could zoom way in on any one of those vibrational levels, we would have a whole plethora of rotational levels. And as we shall discover this semester, the rotational levels spread out as they go up. So if we were to look at a typical energy spacing between these levels, this puts us on the scale of milli electron volts. So 0.001 electron volt. And then finally, if we could zoom way in, way into any of these levels, we would just see there's so many individual translational levels, right, that they form what's called the continuum. Okay. And so this is where we steer or verge away from the quantum world and get into the classical world. Okay. So now how does this connect to the EM spectrum? Well, as you can see right here in our electronic levels, electronic excitation is typically in the visible and also extends down into the ultraviolet and vacuum ultraviolet and even into the X-ray with respect to core electron excitation. So we'll say from X-ray all the way through to visible radiation. So now, as you can see here, our molecular vibrations are occurring in the infrared scale. And maybe you remember that from your organic chemistry. Our rotations, the way molecules rotate about some axis, puts us into the microwave. Okay. And beyond that, our translational modes, those are related to thermal energy, if you recall from our section on thermodynamics. So now just kind of reviewing and remembering what a absorption or what an emission spectrum is either way. So it is really the difference between two energy levels, right? So for example, if we have an electron crash from level 3 to level 2, light will be emitted that has the energy that is the difference of those levels. Okay. And also recall from the relationship E equals hc over lambda, the bigger the energy of that transition is, the smaller the wavelength. Okay, so pictured down here, this is a UV vis spectrum of SO2 in the gas phase. And there's several features here to point out. For one, this main peak right here that I'll highlight at around 280 nanometers, that corresponds to an electronic transition. So I'm just going to draw like an arbitrary energy level diagram here. So that main feature at 280 nanometers or so is from an electronic transition. Okay, so that's electronic. But now you might notice, for one, that it's not like this singular sharp peak. There's this like distribution, okay? And superimposed on top of that distribution are all of these really sharp lines. So once again, I noted if we zoom in on any one of those electronic levels, we will find a whole plethora of vibrational levels. So what we're seeing with each of those individual spikes are multiple transitions to various vibrational levels. I'm sorry for the sloppiness of this. And then if we could zoom even further on any one of those peaks, we would also find a whole series of rotational levels corresponding to even finer structures. So we have the electronic, we have the vibrational, and we have the rotational. Sorry, my handwriting hasn't improved over the year. But you can see in the spectrum, we get all three of those are resolved if we had a high enough precision spectrometer. And then finally, the last thing to talk about in this slide is if we think about now what happens to temperature, and remembering our statistical mechanics, the higher the energy of a state, the lower is its population. Okay? The higher the temperature of a state, the lower its population. And more states are populated if they are closer together. So if we back up here for a second, we can see that there would be many, many, many rotational levels, because the rotational levels are so finely spaced that there is a large population of those at room temperature. On the other hand, there's only one population of electronic states at room temperature, predominantly in the ground state. And as you recall, the vibrational state, most of the molecules are in that ground state. However, there are a variety of transitions available, as we shall see in the electronic vibrational excitation. So if we go back to the slide now, and remembering at 0 Kelvin here, at 0 Kelvin, every single molecule, I really should say electron, will be in the ground state. At room temperature, we would expect some type of population, some type of distribution. And so that will take on some type of Boltzmann distribution. So the amount of shading I'm putting in here corresponds to how populated the state is, right? So if we graphed it, we would see some type of distribution corresponding to some maximum populated state. And if we could achieve such a thing as infinite Kelvin, then technically all of these states would have uniform population, right? They would all be fully populated, which, as we might imagine, is not possible. But we can see that would be the case as we approach higher and higher temperatures.